I was hoping to not have to do this, but it looks like I'm going to have to. In order to have any idea how to wire up these super variable, meaning very different from one another, photoresistors, we're going to have to look at how each one behaves. So first, let's get an idea of what the resistance is for this particular sensor. So when there's a light on the resistor, it's got 680 ohms. But if we cover up the resistor, this particular one only gets to about 5 kilo ohms. And therein lies the problem. We need to match these variable photoresistors with another resistor in order to get the clean 1-0 signal into each digital port. To do that, we'll need a calibrated light source. We're going to take this white LED and put it in this little tube that we 3D printed so that we get a nice consistent amount of light over each sensor. But we don't want to put so much current through this LED that we burn it out. It's going to be in this tube after all. We need what's called a current limiting resistor. What I have here is a battery pack powered breadboard with the batteries underneath, and you can check our link in the description for the Thingiverse model on this. And what this allows us to do is wire up several resistors of different values and see their effect on the brightness of our light. Which one gives us the brightest light? That one, or that one? That one's clearly the dimmest. The reason these are different brightnesses are these resistors are different values. Well, what value is a resistor? It's hard to tell by looking at it, but each resistor has a little tiny set of color bands on it. And while you can certainly refer to your handy-dandy pocket reference for the resistor color codes, it's much easier to use a little cheat sheet like this. For example, this first resistor is red, 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 and that should match out to 2200 or 2200 ohms of resistance. Let's check that. And what do you know? It's 216. The reason it's not exactly 220 is because it's hard to make a resistor that's very, very close to that value. So most resistors are either plus or minus 5%, plus or minus 10%. This blue one here is plus or minus 1%, which means it's very, very close to its intended value. And this variability amongst the actual components, not just our photoresistors, but our other resistors, is why there's a difference between simulation and the real thing. So that one's 2002, and it's got a gold tolerance. The resistor tolerance of gold is plus or minus 5%. This one here, it reads an entire 38 ohms. So this is very, very low resistance. That's going to create a much brighter LED. Orange, white, black. So 39 is what it's supposed to be, and it reads out at 38.3. But again, it's got a gold tolerance band, so that means plus or minus 5%. Now let's check the third one. 327 ohms, and it's color banding. Really hard to see. That's why it's best just to measure them. So to put these in order from lowest to smallest, this one was 38 ohms, this one was 300 ohms, and this one was 2200 ohms. So greater resistance should be dimmer light. This, by the way, is the second version where the LED is built into the case, and it's using my thin board PCB replacement for using liquid solder, cold liquid solder. Some experiments I haven't gotten to yet. So again, up in the Thingiverse if you'd like to grab that. Also on TinkerCad. So again, let's take a look. If we connect it to that one, it should be the brightest. Oops. Helpful to turn it around and put it in correctly. So there's super bright. There's kind of middle. And there's kind of dim. So really, we're just interested in one that will limit the current so we don't burn this out. Well, how would we find out which LED or which resistor value is good for which LED? Well, unfortunately, that information is a little too new for a pocket ref from an electronics store in the 90s. So instead, we will do what everyone does nowadays and Google it. So we've got a 6-volt supply, a little bit more than 5 volts. But if we're using a white LED in the 5 volt range. We probably want a 68 ohm resistor. So that said, I can get away with the 300 ohm. I found this old cable from a box of old electronic parts. Don't know what it's for, but it looks like it'd be convenient for connecting up to a breadboard. 9-pin. It would also be convenient for connecting up a separate sensor bar to the board. So I think I'm going to save one of these. Here it is, all hooked up and powered up. We've got our calibrated light tied to this button so we can see the value. So if we use this to cover our sensor that we are measuring both analog and digital, you can see we get a very, very low number because it's being covered. But when the light turns on, we get a clear 1 and a clear high number. And so that's our eventual goal. Our real goal is to make sure that each one of these sensors, we'll have to do them individually. Each sensor individually has a matching bias resistor, these guys down here, so that we get a clean 1 and 0 on the digital end. And we'll do that by measuring their analog values in parallel just to see what values we need down here. Be sure to like and subscribe and all like that, and we'll get into the rest of how this board was set up and coding it in the next ones. Bye.